Hello everyone, this is Aravind C of 8th semester from Computer Science Department, RYM Engineering College. This seminar is about edge computing, security, state of art and challenges. And under the guidance of Saba Begum, Assistant Professor, Department of CSC, RYM Engineering College. These are the contents. Let's get started by a brief introduction. Cloud computing has revolutionized how people store and use their data. However, there are some areas where cloud is limited. Latency, bandwidth, security, and a lack of offline access can be problematic. To solve this problem, users need robust, secure, and intelligent on-premises infrastructure for edge computing. Let us look at the limitations of cloud computing that gave rise at the edge computing. The first is location unawareness. In edge computing, depending on location, the accessibility rate will be increased. If we want to retrieve any information from IoT devices, it takes much time in cloud. But by using edge computing, retrieving information is very fast. It can be done in a fraction of seconds, depending on your location. And the next, bandwidth shortage. Edge has a sufficient bandwidth when compared to the cloud. Cloud costs more in order to use the services. Lack of real-time services and lack of data privacy. Edge computing definition and reasons for its growth. Basic idea of edge computing is to employ hierarchy of edge servers with increasing computation capabilities to handle heterogeneous computation tasks offloaded by low-end IoT and mobile devices called edge devices. Edge computing provides location awareness, sufficient bandwidth and reduced latency, real-time service and offline operation, privacy savvy, low-cost services. These lead to its rapid growth. And the next, the recent statistics of the edge computing. We know that edge computing started in 2018, and before that we were using hardware in 2016 and 2017. As we see a blue layer starting from 2018, that is when it came into existence. And the use of edge computing goes on increases till 2025 according to the recent statistics. And next, the security issues. The security requirement for edge computing starts with hardware root of trust. There are 4 types of attacks that account for 82% of edge computing devices. Those are: the first one, distributed denial of service attacks, which is nothing but DDoS attack. And the second, the side channel attack and malware injection attack, authentication and authorization attacks. Let's get into the first one, DDoS attack. IoT device is requesting the server in order to get the data or computation. This device wants an computation from our platform. When it is requesting, the attacker before the target edge server provides the services, the attacker attacks the server by requesting it. As you can see the figure, the attacker attacks the server by requesting it, and the device by clarifying and satisfying the requests of the attacker, the edge server loses its hardware power. Then it could not be able to provide services to the original device. That's the DDoS attack. And the next one, side channel attack. A side channel attack, we can say it as an indirect attack. Instead of attacking directly to retrieve the private information, the attacker first attacks the publicly available information, and then through it attacks the private information and gathers the secure details. This is how the side channel attack works. And this is the diagram. This is how the attacker attacks the publicly available information, and through that it can access through the private information. And the next, malware injection attack. Malware is injected or installed into computing system. These types of attacks is threat to system security and data integrity. If the computational power is available up to high performance, then malware injection is not always feasible and possible. Edge devices and the low-level edge servers can be protected by traditional firewall and hence are more vulnerable to the malware injections. And this is how the attacker attacks the edge devices and the edge servers by injecting a malware into the devices. And the next, the authentication and authorization attack. Authentication is an action of verifying users identifies who requests certain services. In edge computing, authentication is generally performed between edge devices and the edge servers. According to the diagram, as attacker cannot access to the authentication and authorization systems, the attacker attacks the edge computing devices and through that it accesses the authorization systems. So the main thing is in this is the hardware must not be attacked. If the hardware is attacked, then it will become easy to the attacker to access the authentication and authorization systems. These are the causes of security threats: weak computation power, attack unawareness, OS and protocol heterogeneities, coarse-grained access control. Let's get into the first one. Weak computation power. In edge computing, the computation power will be usually weak than cloud. It is so that the edge server is more vulnerable to attacks, and edge devices have flexible defense system due to which attacks which may be inefficient against some computer may also cause serious threat to the edge devices. And the next come attack unawareness. Here let's say some IoT devices may not have a GUI interface. When we use such devices, we may not know whether the device is in which state, either in a stop state, start state or in a running state. So without user interface, we will not get to know. Then the user may have limited knowledge about running states of devices, whether it has been shut down or compromised. And the next one, OS and protocol heterogeneities. As most edge computing devices have different OS and every OS have their own protocols, due to which there will be a lack of standardized regulation. This problem directly leads to difficulties of designing unified protective mechanism for edge computing. And here are the few operating systems used in edge computing. Next is the coarse-grained access control. The access control model designed for the general purpose computers and cloud computing mainly consists of 4 types of permissions: no read and write only, and read and write. Coarse-grained access control models would never be satisfiable in edge computing due to the more complicated systems and their enabled applications. So here coarse-grained which means that accessing multiple data at a time, and the fine-grained which means that accessing single data every time. So what the sentence means is accessing multiple data at a time is more better than accessing single data every time. Current access control models are mostly coarse-grained. Here the status, QUO and grand challenges in securing an edge computing system. There are 2: lacking consideration of security by design, fragmented and coarse-grained access control. Lacking consideration of security by design. The primary goal of edge computing is to provide a more efficient and lightweight computing platform for emerging applications such as IoT and smart cities. Therefore, designers tend to focus more on performance rather than security when designing an application-specific edge computing architecture. Such an inefficient consideration of security by design directly exposes the edge computing infrastructures to broader attack surfaces. And the next one, fragmented and coarse-grained access control. Current access control models are fragmented because different edge computing scenarios may adopt different access control models that may be designed in totally different manners with respect to permission, segregating, granting and accessing. This situation inhibits the development of a unified and manageable access control framework for various edge computing systems. Current access control models are also coarse-grained, as fine-grained permissions are complex and underexplored. Here are the benefits of the edge computing. So speed, as we know that edge computing has high speed than the cloud computing, and also in the security wise it is highly secured. Scalability, versatility and reliability. And these are some applications. There are three applications of edge computing: a tool to gather massive information from local things as an aggregation and control point, and the second one, a local storage and delivery provider or of bandwidth intensive content as part of a content distribution network. On an on-premise application and process tool to replicate cloud services and isolate the data center from public cloud. Some other applications: 5G applications and smart cities. 5G applications. The responsiveness and bandwidth are going to be expected to be significantly high, as 5G communication is projected to perform upwards of 100 times faster than the 4G. This implies you will be able to download a full HD movie in a very few matters of seconds. To achieve these small data centers will be required. Edge computing will play a pivotal here. Smart cities. It will be a connected world out there, which will be based on reliable sensors, storage and security. From transportation to buildings to streetlights, everything are going to be connected. Even your homes will become smarter. Every application should have a robust responsive system, and edge computing can make smart cities a hit. Real-time applications on edge computing. Oil and gas remote monitoring. Whenever there is a leakage of harmful gases in industries, IoT devices which sense this leakage need to retrieve information about safety measure to be taken, so as to overcome the disaster situation immediately. Edge computing is one such technology which provides easy access of information as it makes use of offloaded computation. And these are the references. Thank you.